Welcome to STEM Talk.
STEM Talk. STEM Talk. STEM Talk. STEM Talk.
STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society. Hi, I'm your host, Dawn Carnegas, and today we have a terrific interview with Dr. Michael Turner, who will discuss some of the most mysterious aspects of our emerging understanding of the universe, dark energy and dark matter, which together account for most of it. Also joining us is Dr. Ken Ford, IHMC's director and chairman of the Double Secret Selection Committee that selects all the guests to appear on STEM Talk.
Hi, Don. This will be fun today. Now, at first blush, one might think that this will be a rather dry and academic topic. But Michael Turner is exactly the right guy to talk to about dark energy and dark matter. After all, he coined the phrase, dark energy. He is able to explain some of the deepest issues in cosmology with a rare clarity and eloquence. This will be an interesting interview indeed. It is important to note, however, that after we sat down with Michael, Vera Rubben, who Michael refers to in his interview, passed away on Christmas Day. As noted during our interview with Michael Turner, the existence of dark matter had first been proposed by Swiss astrophysicist Fritz Zwicky in the 1930s, but it was not confirmed until Vera Rubben's work. Her obituary in the New York Times accurately noted that her work transformed modern physics and astronomy with her observations showing that galaxies and stars are immersed in the gravitational grip of vast clouds of dark matter. This episode of STEM Talk is dedicated to her memory.
Before we get to today's interview, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to STEM Talk, and we are especially appreciative of all of the blushingly wonderful 5-star reviews that are piling up on iTunes. Of course, the Double Secret Selection Committee has been continually and carefully reviewing the iTunes reviews with an eye toward selecting the best reviews to read on STEM Talk. There are extra points for pithiness, wit, and of course, lavish praise.
Especially lavish praise. As always, if you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk t-shirt.
Today, our winning 5-star review was posted by someone operating under the moniker Bob RXUF. As soon as we hear from Bob RXUF, a STEM Talk t-shirt will be on the way. Here's the winning 5-star review, which is titled, I wish this podcast aired every day.
With all the garbage we are bombarded with, listening to STEM Talk reminds me that there is higher intelligence, the hope for mankind.
Well, thank you, Bob RXUF, and all of the other STEM Talk listeners who have helped STEM Talk get off to such a great start.
Okay, now on to today's interview with Michael Turner.
As you will hear, Michael Turner is a theoretical cosmologist who coined the term dark energy in 1998, and he is a Rauner Distinguished Service Professor at the University of Chicago. He also served as the Assistant Director for Mathematical and Physical Sciences for the National Science Foundation from 2003 to 2006. More recently, in 2013, he was elected as the President of the American Physical Society.
Michael is the recipient of too many awards and honors to recite, so we won't. But suffice it to say that he has, through his own research and through his leadership, greatly shaped the scientific landscape in physics and cosmology. His research focuses on the earliest moments of creation, what is sometimes referred to as the Big Bang, and he has made contributions to inflationary cosmology, dark matter, and dark energy.
STEM Talk. STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
Michael, we want to thank you so much for taking the time to chat with us today on STEM Talk.
Glad to be with you, Dr. Turner. This is Tom. How are you doing?
Good. Nice to meet you, Tom.
We're very delighted to have you. And you've made your career in trying to peel back the curtains on this new cosmic phenomenon called dark matter and energy. Give us the big picture. What do we know about our own universe and how it's structured? And then how did we stumble upon this phenomenon called dark matter and energy?
The headline here would be, there's much more to the universe than meets the eye. And one of the stunning things of the last say, 10 or 20 years is that we've done a census of the universe. And let me just walk you through the census to give you this big picture and then zero in on dark matter and dark energy and in particular the difference between them. So 0.5% of the universe is in the form of stars. The other 99.5 is dark. We don't see it directly with a telescope, but I'll come back to this. We see its influence through its gravity. Atoms account for about 5% of the universe, and only about 1 in 10 atoms is in a star. The rest of the atoms in the universe, stuff that we're made of, the stuff of the periodic table, the chemical elements, that's 5% of the universe, but only about 1/10 of that lights up as stars. And so the other atoms in the universe actually light up in the X-rays, which is a very interesting story. NASA's played a critical role with its X-ray satellites in revealing where most of the atoms in the universe are. They're in hot gas that gives off X-rays. But let me go to the 95% of the universe, the stuff that is dark to all of NASA's satellites, dark to all of our eyes, dark matter and dark energy. And so the dark matter is about 25% of the universe, and it provides the cosmic infrastructure of the universe. The dark matter provides the structure of our galaxy. So our galaxy is largely dark matter, and so our galaxy is held together by the gravity of dark matter. The other 70% of the universe is dark energy. And dark energy is very, very mysterious stuff. It's spread out roughly uniformly. As far as we know, it's absolutely uniformly in the universe. It is actually causing the expansion of the universe. The universe is getting bigger. That's what Hubble discovered. It's what made Hubble famous. But this dark energy is causing the expansion of the universe to speed up, not to slow down, which is really mind-boggling. And so if you come back to the big picture, 5% atoms, 25% dark matter, 70% dark energy, our universe has really been, its evolution has been a battle between the two dark titans, dark matter and dark energy. Dark matter, its gravity holds galaxies, clusters of galaxies. It provides the cosmic infrastructure. And then dark energy, which just recently, 5 billion years or so ago, took over and is causing the expansion of the universe to speed up. So dark matter and dark energy, two very, very big mysteries. We know of their existence because of their gravitational effects. We don't know what the dark matter is. And we, at the very least, it would be safe to say we don't understand the nature of the dark energy, but we know they're both there. And so coming back to it, those beautiful stars that, I bet they just look fantastic from the shuttle or the space station. They look fantastic if you get to a nice dark spot here on Earth. That's just the tip of the iceberg. And until about 25, 30 years ago, we thought that was it, just the stuff that shined. And now we know that the stuff that shines is a tiny fraction of the universe.
So we're familiar with the visible universe and the cosmos, and we really should change our thinking to think of ourselves as like just the foam on the top of the glass of beer, right? We're just a little bit of fluff floating around on this sea of dark matter and energy, it sounds like.
Yeah, there are two ways to look at it. One is to say, oh my goodness, we're such a small part of this. The other is we're a very special part. While our galaxy is held together by the gravity of dark matter, it's the stars that give off light and give off energy, and It's the atoms that we're made of. So we're the tip of the iceberg. We're the special stuff. The dark matter particles, we think dark matter is made out of particles that just don't give off or absorb light. The really exciting thing about dark matter is that we believe that dark matter is a new form of matter that has yet to be produced on Earth. And it's left over from the Big Bang. And one of the big scientific adventures that's going on right now is trying to identify what the dark matter particle is. And not only will it solve a cosmic mystery, but it's going to teach us about the microverse and the elementary particles. And so, for example, you might think of, oh, well, that dark matter, you discovered it with telescopes, and probably you're going to have to figure it out with telescopes. One of the big ways we're trying to figure out what the dark matter is we're trying to produce the dark matter particles at the Large Hadron Collider in Geneva, Switzerland, the world's most powerful particle accelerator. Mm-hmm. Right now, they're running and they're trying to produce dark matter particles. And if they succeed, we may well, in the next few years, be able to say the dark matter is X, Y, or Z.
What was the original evidence that led us to understand that dark matter, a quarter of the universe, was out there, and then accompanied by dark energy? When did we tumble on that fact, and who are the people who made that discovery?
It's a really interesting story, and it's a metaphor for many, many scientific stories. So the first person who stumbled upon it, people didn't really pay attention to him. His name was Fritz Zwicky. It was the 1930s. The study of the universe, cosmology, is the name the scientific name for the study of the origin and evolution of the universe, was young. And Zwicky was studying clusters of galaxies, and he made some measurements and realized that a cluster of galaxies is just a collection of galaxies, and he realized that the individual galaxies were moving really, really fast. They were moving so fast that the gravity of all the stars and all the galaxies was not sufficient to keep the clusters together. And unless there were some other matter there that didn't give off light but had gravity, the clusters would fly apart. And he was kind of a cantankerous guy, very, very, very smart, maybe not the best social skills. And people didn't really pay attention to him. The problem wasn't really, really ripe at the time. As I said, cosmology was young. The universe was incredibly mysterious. Only a few years before had Hubble identified that galaxies were the basic building blocks of the universe. If you go back 10 years before Zwicky's discovery, we only knew of one galaxy in the universe. So cosmology was truly young. Run the clock ahead about 40 years to the work of Vera Rubben, a scientist working at the Department of Terrestrial Magnetism of the Carnegie Institution of Washington, started studying the motions of stars within galaxies like our own Milky Way, and discovered that there was this very same problem, that the stars were moving so fast that without additional gravity, without the gravity of stuff that couldn't be seen, our galaxy would not hold together. And so she showed that there's a dark matter problem in our own galaxy, or a dark matter opportunity. And this really brought the problem home. It said that it wasn't really so exotic. It was our own galaxy would not hold together if it were just the gravity of the stars in it, that there must be some dark matter. And that really got things going. People really started paying attention to this problem. And, once you focus in on something, particularly that makes up 25% of the universe, the evidence just started to pour in. Every direction you looked, you would find evidence for dark matter. And dark matter went from not even being on the astrophysicists' most important list of problems to solve to being at the very top of the list.
So when I think of the galaxies in the universe, I think of these great gulfs of empty space between the galaxies and their billions of stars. And yes, there's gas drifting in interstellar space and so on, but you think of this immense emptiness, and yet you sound like you're saying that dark matter is permeating all of this great space in our cosmos and sort of holding things together, making the clock tick. Is that right?
Yeah. And in fact, what's really interesting about this is people originally talked, Immanuel Kant was the first person who talked about galaxies in the universe being made up of galaxies. The evidence didn't come until Hubble in the 1920s, but he called them island universes. And if you look at, for example, the most iconic picture in all of astronomy, the Hubble Deep Field, where Hubble just pointed in one direction and surveyed a tiny patch of the sky, you see several thousand galaxies, and they really look like islands. If you could see, and we can't quite do this yet, but if you could map out the dark matter, what you would find is that these galaxies that seem to be little islands that are separated are connected together by a web of dark matter. And in fact, now that we understand dark matter a little bit better, we think of the universe as being a cosmic web of dark matter. And I'm gonna be a little artistic here, decorated by stars. So the galaxies look quite separate, but the cosmic web of dark matter, we're all connected, and the dark matter from the individual galaxies overlaps and is connected, and it's a cosmic web of dark matter that we can't see with our telescopes, although we're beginning to map out this cosmic web of dark matter.
You mentioned that all of this began at the same time as ordinary matter that we can see back at the Big Bang. Was this a theoretical prediction of our understanding of the genesis of the universe, or was this empirical evidence for dark matter just discovered, and then we had to go back and change the equations to account for its presence?
Well, so the dark matter is a little more linear in its scientific process, in the sense that Zwicky and Vera Rubben and others provided the evidence for it, that there's something out there that doesn't give off light, and but we feel its gravity. So that's a nice story. And so in science, then you start making up a list. What could it be? Could it be dust? No. If it were dust, there'd be so much of it we couldn't see out of our own galaxy. Could it be faint stars? And actually, the Hubble Space Telescope answered that question with the Hubble Deep Field. If it were faint stars, we would have seen them. And around 30 years ago, around 25 or 30 years ago, we started assembling the case that we have right now, which is, you know what? We've done an accounting of the amount of ordinary matter in the universe, and the ordinary matter in the universe can only contribute about 5% of the total, yet dark matter is 30%. So we had an accounting problem now that the total amount of matter in the universe is much greater than what atoms can contribute. And so it must be made out of something other than atoms. And we started with neutrinos. Many people may have heard of those mysterious neutrinos, one of the elementary particles that we do know of. There's lots of them in the universe. And in the 1980s, we know neutrinos have very, very tiny masses, but there's so many of them that if they had a mass basically 1 million times smaller than that of the electron, they could account for the dark matter. We now have firm evidence that neutrinos have masses, but their masses aren't big enough so that they're the dark matter. And so we're now trying to zero in on what new particle it is, and that particle would be left over from the Big Bang. And so a couple of the candidates I'll talk about one of them called the neutralino. It's got a very funny name. The neutralino, we can calculate how many neutralinos would be left over from the Big Bang. And one of the things that tells us or suggests to us that we might be on the right path is when we calculate how many neutralinos there would be left over from the Big Bang, the number we get is about the right number to explain the dark matter. And so we're in the midst of this detective story. We've ruled out the neutrino as being the dark matter. That would be fairly exotic. And it's something else. We have some circumstantial evidence that it might be this particle called the neutralino, which, by the way, has not been proven to exist. It would be the lightest of a new class of particles called supersymmetric particles that are predicted by string theory, that they're trying to verify their existence at the Large Hadron Collider. So we're in the midst of this detective story where we're trying to figure out what the dark matter is. At this point in time, we do a better job at saying what it isn't. So it isn't atoms, it isn't neutrinos. We think it's yet a new particle. And we feel like we're close to solving this mystery.
Wow. So we actually have the facilities that could attack the very nature of this neutralino particle. It seems to me that it's such a difficult concept to grapple with, and it's hard to cross over from our visible universe to dark matter. But it's interesting that we might already have the machinery to do that. Is that right?
That's right. So astronomers, not normally interested in the microverse, are very interested in what's going on at the LHC, because at the LHC, they have the possibility of actually producing the dark matter particle. And I mean, that would be as mind-blowing as it is that the universe would be made of more than just the atom, of different stuff than we are, to be able to say, and we produced it at the Large Hadron Collider. And I am going for a triple signature because there's two other methods that we can bring Marshall to figuring out the dark matter. And these dark matter particles that would be make up the infrastructure of our own galaxy, they can occasionally bump into one another, annihilate, and transform into forms of energy that are easier to see, like gamma rays. And so NASA has another satellite up there called the Fermi Gamma Ray Space Telescope. I might have missed some of the letters there. And it has a tantalizing signal from the center of the galaxy that can't be explained by astrophysics. So it's not a black hole, it's not a neutron star. And that tantalizing signal could be dark matter particles annihilating and transforming into gamma rays. And that's something currently under study. But wait, there's more. We would like, I said, a triple signature, so we can build very, very sensitive detectors. These dark matter particles are very shy, and so we can build very sensitive, we can and have built very, very sensitive detectors to detect the dark matter particles in our halo. And just to calibrate people's thinking, if you've got a coffee cup in front of you, at any given time, there's one dark matter particle in it. And so big detectors now approaching multiple tons are deep underground where they're shielded from cosmic rays to try to detect the telltale signatures of dark matter particles going through them. So I am hoping that, say, 5 years from now, maybe 10, that we would have a triple signature of dark matter and be able to give you a name. And I would love, of course, Zwicky's no longer with us, but it would be great to tell Zwicky, you know, we figured out what it is, and the solution was even bolder than what you thought.
STEM Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research lab pioneering groundbreaking technologies aimed at leveraging and extending human cognition, perception, locomotion, and resilience.
Michael, assuming that over time our understanding of dark matter and dark energy continues to advance, can you envision future applications of this knowledge?
The biggest implications of the kind of research that I'm involved in and many others are involved in are the ones that you can't imagine. And so let me try a little bit to imagine it, but I'll do a really bad job. So if this is indeed the neutralino, this would be the first evidence for this theory called superstring theory that unifies all the forces. It's a very, very bold theory that says, among other things, that there may be additional dimensions of space-time, that we may live in a multiverse. And so it sounds like I'm even going farther from the practical. But I'll bring this back to a theory that still mystifies people, called quantum mechanics. So about 100 years ago, we realized that the subatomic world is governed by a different set of laws than the macro world that we live in. And that's quantum mechanics. And I think quantum mechanics 100 years ago was probably even more mysterious than dark matter. Certainly the evidence would have been harder to explain for it. And today, 40% of our GDP is based upon quantum mechanics. And the reason I say that is we live in the information age, and quantum devices store information, they manipulate information, they transmit information. Without these quantum devices that, and what I'm talking about are computers and digital cameras and the internet, all of those, if I turned off quantum mechanics, none of those would be possible, including this conversation that we're having over Skype, including you recording this conversation. And so 100 years ago, I don't think if you'd ask someone studying quantum mechanics, they would say, oh, we're really doing this just to understand nature. And I cannot imagine any practical consequence of this. But I suspect if history is any guide, every time we understand nature a little bit better, there will, in the long run, be spin-offs and practical applications that change the way we live and hopefully improve the way we live.
Good. Now we've been tiptoeing around the big the big gorilla in the universe. That's dark energy, because it makes up most of our universe. So let's talk about that a bit. And you mentioned at the top of how dark energy appears to be accelerating the expansion of the universe. And I've always been dissatisfied with the idea that the universe is endlessly expanding and everything is getting farther away from everything else, because it doesn't seem to end very nicely for us inhabitants of the universe. And perhaps you can fit this the observed expansion of the universe into how dark energy might be causative and how we can grapple with dark energy and detect it.
Well, as you said, the one of the fundamental questions about the universe once the expansion was discovered was, will the universe expand forever? And I think everyone can appreciate that as the universe expands, gravity should be slowing it down. Gravity is an attractive force. It's what holds us on the surface of the Earth. It's what holds the planets in orbit around the sun. And so a big question in cosmology was, at what rate is the universe slowing down? And is that slowdown sufficient so that the universe eventually recollapses? And that's a very hard question to answer, but it was finally answered in 1998. Two teams were trying to measure the cosmic slowdown, and both teams got a big surprise when they found out that the slowdown was actually a speed up. And now I'm going to put a little asterisk here. That might suggest that we're doomed to expansion forever. And in fact, I'll come back to that if we have time, that actually what it says is we're back to the drawing board on the ultimate fate of the universe. But let me talk a little bit about how it could be that the expansion of the universe is speeding up. And one of the remarkable things about Einstein's theory of general relativity, which is our current best understanding of how gravity works, everyone's heard that, general relativity says that space-time is curved, and so that's how gravity works and all that. And also, one of the predictions of this theory is that it is possible for gravity to be repulsive. And I don't mean the study of gravity. I mean actually gravity itself. And that seems like the world's biggest oxymoron because, when you think about gravity, its defining feature is that it's attractive. But according to Einstein's theory, if you have weird enough substances, their gravity, their gravitational effect can actually be repulsive rather than attractive. And that's what we think we have going here. And that's what we think this dark energy is stuff that is so unusual that its gravity, rather than being attractive, is repulsive. And so this dark energy and the amount of it needed to account for the speed up of the universe would be that it's 70% of the universe and it's spread uniformly everywhere. Its repulsive gravity is causing the universe to speed up. Now, before I hand it back to you, I just want to say if people are confused with the concepts here, if you're confused with this concept, you've caught up with us. So I like to call this the most profound mystery in all of science. How it is that there's something filling the universe whose gravity is repulsive, and what is it? It is a very big mystery. Right now, we're kind of at the Zwicky time, if you remember the dark matter puzzle, that 80 some years ago, Zwicky found that there weren't enough stars and clusters of galaxies to hold them together. We found the rudimentary evidence for the speed up of the universe, and so we've named the stuff that's doing it. We've called it dark energy, and other than that, our understanding is we're confused. But this stuff is obviously very important because it has the destiny of the universe in its hand.
At your recent lecture at IHMC, you said that dark energy might not be energy at all, but some new aspect of gravity that we don't understand. Can you elaborate on that?
In the lecture that I gave there, I also pointed out that we're very early in this game, and while Einstein's theory provides a possible explanation for the speed up, namely that it is the repulsive gravity of dark energy, maybe the fault is not dark energy, but maybe we're seeing a breakdown of Einstein's theory of gravity. Most scientists believe that Einstein did not get the last word on gravity. His theory of how gravity works was a great advance over Newton's theory. It revealed many new things to us: black holes, gravitational waves, things like that. But it does not incorporate quantum mechanics. And so we believe that there is a theory that is even grander than Einstein's theory. And maybe that theory will say, look, there isn't any dark energy. We're just seeing an effect of this new theory that as the universe thins out after it's expanded for 15 billion years, it starts to speed up. And I didn't mention that with dark matter, but there was a point in time where in trying to understand dark matter, we said, maybe there's no dark matter. Maybe we've just discovered something new about gravity. That does not look like the solution to the dark matter problem, but it could be for dark energy. So this is a big, big mystery. We're at the very, very beginning of trying to understand this. And often at the very beginning, you cast your net widely. You're very confused. We're definitely very confused. We're trying to cast our net widely to understand this phenomena.
Is there a link between this dark energy and its expansion effect and its its repulsive properties and gravity waves? Is that one way for us to get at the nature of dark energy?
Don't know. Whether or not they have anything to do with dark energy, I don't know. And at this point in time, anytime somebody says, "Could that have something to do with dark energy?" Generally, my answer, and that'll be my final answer here, is could be, because it's such a big mystery, and we really are struggling to get our heads around it. We're looking for all possibilities and all possible clues.
What kind of reception to NSF research in these kinds of topics have you received from Congress, in your opinion, or observing how the Congress has funded NSF in recent years? Are we doing this at the right level, or does this need to double in size in terms of the budget?
Well, if you ask a scientist funding for basic research, the answer is always more. And I think there is a real appreciation that crosses the aisles at Congress of the transformative power of science. And so I think both sides have agreed on that. And when I was at NSF 2003 to 2006, and we saw both sides working on science and increasing the funding for science and really appreciating it. In recent years, I don't think there's been less of an appreciation for the importance of science, but other issues have gotten in the way. And so we've lost our way a little bit. And the hard question you asked that I've danced around here, which is, let me put my hat on as a policy person rather than a science person. And that question is, what is the right amount? So if you ask a scientist, the answer is more. And but if you say, gee, could you be a little more quantitative? So is it twice what we have? And it's a very, very hard number. Almost every country on Earth is grappling with it. And each country looks at all the other countries. When we look at Asia, we get very, very nervous. Korea, China are ramping up their funding of basic research. And when I just got back from a trip to China, and I can't believe their ambitions. They have very, very big ambitions. Now, if you compare where we are to where they are right now, we're far ahead of them. But if you look at the increases that they're doing, the same is with Korea. And some of the European countries fund science at a higher level than we do. And I don't think anyone knows what the right level is. Right now, if I would say the biggest disappointment is that we haven't had a coherent policy. So the funding has gone up, it's gone down a little bit. The biggest impact of this is discouraging the next generation of scientists. So at NSF right now, the biggest number, if you ask me, are we funding at the right level? The biggest number that would tell me we're not is the success rate. So the success rate for for a scientist submitting a proposal at NSF, only 10% of the proposals are funded. 90% are rejected. And you might say, well, maybe those 90% aren't very good ideas. And you look at those 90%, and some of them aren't very good ideas, but the bulk of them are extremely good ideas. And we're discouraging the next generation of scientists who, if you look at it from their perspective, to get one grant, they have to write 10. And that's a crazy system. It's wasting everybody's time. It's wasting the reviewers' times. And so I think NSF, something is not healthy right now when you have a success rate as low as 10%.
A couple of questions I have based on this topic is, is there a particular sector of funding in terms of cosmology that needs to be enhanced? In other words, do we need to build a new facility of some sort, whether it's a telescope or a detector, to compete in this area for our young scientists? Or is it just more general support of research and analysis funding?
Oh, boy. So the hardest, I already punted on the hardest question is, are we funding enough research? And the even harder question is the balance, is the portfolio. Should we be funding more here than there? And the one answer I would give is an area that I think really is suffering is astrophysics, and not just because I'm an astrophysicist. And that area of science, there's just been an explosion, not just dark matter and dark energy, but there's been an explosion in our ability to explore the universe. And the funding has not caught up with the growth of that area at NSF or even at NASA. And so I would say that that's an area that's just exploding, and we're not taking advantage of all the opportunities. And then the harder question has to do with leadership. So one of the things that we're facing, one of the American, the last 50 years of the 20th century were American dominance in all areas, particularly in science. And we did such a great job. We were such responsible stewards that we allowed 1,000 flowers to bloom. We allowed Asia to blossom and Europe to be rebuilt. And so now the scientific world is flat. And finding our place in a scientific world where we're not going to dominate every area is really vexing. So we're not always going to have the most powerful accelerator. We're not always going to have all the big telescopes. And so what exactly is our place in that world? And of course, Tom, you know that the European capabilities in space, just in your time at NASA, increased dramatically. The European Space Agency, their ability to launch satellites and mount big missions. And that's great for science, that's great for the world. But we also want to make sure that we don't cede the leadership, that we continue to be a big player. And of course, the James Webb Space Telescope, that's a very exciting project. It's big and bold and complicated and really hard. And as I've said in several editorials, this is the kind of project that only this country can do. And when it's successful, we will be proud of it. The world will say, oh my goodness, it will be as transformative as the Hubble. So we're still doing these big and bold things, but we're doing it in a world where other nations are capable too. And finding our place, I think we do want to continue to be leaders. And that's going to require a different kind of vision. We can't outspend the rest of the world, but we can lead and with our vision.
Michael, what led you to become a cosmologist and study some of the biggest questions that humans are able to pose?
So I was led to a career in science by great high school teachers who nurtured my interest in science and showed me the possibilities. And so teachers are so important. And I think that I cannot imagine a more interesting career for anyone to pursue. And so any young person who's thinking about it, boy, the opportunities to understand nature, to help solve, we've been talking here about the mysteries of the universe, and I've struggled with practical applications, but just about every challenge that our country and the planet have involves science. And trying to understand the secrets of nature and trying to solve the most vexing problems of mankind are really, really exciting. And so I think the career opportunities in science are at least as good if not better than they used to be. And it's a very rewarding career. I mean, it may not be financially rewarding, but I'll just talk personally. I get to think about the mysteries of the universe. I get to think about how the universe began and how it will end. Are we alone in the universe? And boy, that's a pretty good job to have. We often call astronomy a gateway science, that we're the Pied Pipers, because the questions that we're asking, how did the universe begin? Are we alone in the universe? What's the universe made of? What's its ultimate fate? Boy, those attract anybody's interest. And then once you get sucked in to try to answer that question, then you realize, well, you got to learn a little bit of math along the way. And of course, once you're hooked on trying to answer a big question, you're not going to let anything get in the way. You're going to learn the math you need. You're going to learn the physics you need. You're going to build the instruments that you need to build. And so sometimes the big questions get people hooked. Rather than saying, gosh, would you like to do this algebra homework? which actually I used to love doing my algebra homework. But you get hooked on these big questions in science. And once you're hooked, you'll do anything to get to the answer, even if it's this math that you didn't think you'd like. So that's one trick, is misdirection. Get them interested in science, and then they'll realize, well, the language of science is actually math, and they'll be explaining to you why they want to take math courses.
I got my first telescope when I was 12 years old, and that was a testament to the fact that astronomy is one of those gateway sciences and ways to get people to think about a career in science. I certainly wanted to be an aerospace engineer or a space scientist as I was growing up, and whatever I could do to get into the space program was the thing that was driving me from astronomy to aerospace engineering and even flying later on. So it was all of it involved math, and all of it involved the physical sciences and engineering. So get hooked early and you'll never look back.
Said well.
STEM Talk. STEM Talk. STEM Talk.
STEM Talk.
Wow, what an interesting interview. I love the mind-boggling statistics that we heard, that 99.5% of our universe is dark, comprised of either dark matter or the even more mysterious dark energy. To recap the big picture, our universe is 5% atoms, 25% dark matter, and 70% dark energy.
I love Michael's turn of phrase. He must be a terrific professor. Mm-hmm. During our interview, he referred to the evolution of the universe as a battle between the two dark titans. Gotta love that.
Love that.
Later, Michael says, we think of the universe as a cosmic web of dark matter, decorated by stars.
Great stuff. I invite you to visit the STEM Talk webpage, where one can find the show notes for this episode and for all the others, stemtalk.us. This is Dawn Carnegie signing off for now.
And this is Ken Ford saying goodbye until we meet again on STEM Talk.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.